As a high school student or even a chemist, titrating on a harder level is a necessary skill to know. In this video, I'll be attempting and most likely failing to perform a titration. The investigation being conducted is a redox titration to find the amount of iron present within each tablet. Now you may be asking what that is and how it works, and to answer your question simply, a redox titration, unlike a traditional acid-based titration, measures the point at which a redox reaction is complete. This means that in a redox titration, the unknown substance is being oxidized and losing its electrons, while the known substance is being reduced and gaining electrons. Once the unknown substance has no more electrons left to give, the endpoint is reached. This will be indicated by the presence of the known substance starting to take over the solution. In this investigation, the unknown substance will be Fe2+ solution, and the known substance will be the potassium permanganate solution. As the Fe2+ loses its electrons and becomes Fe3+, the manganese will go from a 7+ charge to a 2+ charge. Once all of the Fe2+ has turned into Fe3+, the presence of potassium permanganate will indicate the endpoint of the reaction, requiring no indicator. For this investigation, we will start by identifying some important information, such as the inquiry question, hypothesis, and variables. Our inquiry question is it possible to identify the amount of iron present within off-the-shelf iron tablets to the accuracy of the label? Our dependent variable, or what we're finding, is the amount of iron or Fe2+ present in each tablet. Our independent variable will be the brand of iron tablets used, and finally our controlled variables will be the concentration of potassium permanganate and sulfuric acid, number of tablets used per brand, and the same iron solution when repeating the experiments for reliability. Before conducting the experiment, I have predicted that the results achieved will not be accurate or near the actual mark, as I in no way have any experience in this. The materials required for this titration will be a 50 ml burette, 25 ml pipette, 3 250 ml beakers, 250 ml conical flask, 2 250 ml volumetric flasks, funnel, potassium permanganate, sulfuric acid of a strong concentration, retort stand, burette clamp, and 2 brands of iron tablets. It is important to note that due to its strong corrosive qualities, exposure to potassium permanganate solution can cause skin and eye irritation. To avoid this, wash hands immediately after any spillage to reduce any chance of contact. Make sure to handle it carefully and do not make any direct contact. Sulfuric acid is also really dangerous. If sulfuric acid makes direct contact with the eyes, it can cause permanent blindness. If ingested, this chemical may cause eternal burns, irreversible organ damage, and possibly even death. Exposure to sulfuric acid aerosols at high concentration leads to severe eye and respiratory tract irritation and tissue damage. To avoid this, make sure to handle with care and wash hands after usage. Deal with any spillage straight away to minimize any skin contact. Make sure not to smell acid directly and do not make any direct contact. PPE such as glasses are necessary. And finally, the last dangerous item is any glassware, as it can be easily broken and cause cuts. To avoid this, handle with care as glass is very fragile, and clean up any breakage immediately. Now, before the actual investigation is conducted, it is important to do some beforehand calculations for preparation. We need to start by identifying our two half reactions. Our oxidization reaction balanced out should look like this. This is just showing the change of Fe2+ to Fe3+ and the loss of an electron. Our reduction reaction balance should look like this. This is just showing the addition of electrons in the manganese, changing it from a 7+ state to a 2+ state. If we combine the equations, we end up with this. This is just the previous equation combined with electrons from both sides cancelled out. This shows us the molar ratio between manganese ions and Fe2+ ions, which is crucial to the calculations later on. This also allows us to kind of see what will be happening. Now that we have all of that out of the way, we can start by preparing the iron that we will titrate. For this, we need to weigh out 10 tablets on a scale and note down the weight in our logbook. We then proceed to crush up the tablets using a mortar and pestle till they become a fine powder. Empty the contents of the mortar and pestle into a beaker and rinse out the mortar with the sulfuric acid. Mix the solution and then pour into a volumetric flask using a funnel and fill up to the mark. Shake the flask around and leave it to sit for approximately 2 hours so the sulfuric acid can break the tablet down completely. In the meantime, we can start to prepare the potassium permanganate standard solution. For this, you can start off by measuring out any amount of potassium permanganate into a 250 ml volumetric flask. I ended up using 0.3 grams as a strong concentration of potassium permanganate will be needed to titrate the iron solution. After the potassium permanganate is measured out, you can fill the volumetric flask up to the mark with distilled water. Once this is done, we can start to set up the burette. We start off by setting up a retort stand with a burette holder. I had to use a clamp under my burette holder because it would not stay in place and there was no other holder available, so I decided to make do with what I had. Place the burette in the holder and place it under a waste beaker. Start off by rinsing the burette twice with distilled water and then once with potassium permanganate using a funnel. This is done as a precaution to make sure the distilled water doesn't dilute the standard solution and allows for accurate results. After cleaning the burette, take out the funnel and release a little bit of the solution to get rid of any air bubbles in the burette, measuring the initial volume after this. Now going back to the iron solution that should have been dissolved by now, we will first dilute it because 18 mol solution is pretty hard to titrate, so we will dilute it by a tenth. So take 225 ml of the solution using a clean pipette that has been rinsed with the solution it will contain and empty it in a 250 ml volumetric flask, and proceed to fill the flask to the mark. This will now make the solution 1.8 molar and will also be worth 1 iron tablet, which is important to know for later. Now with the pipette that has been pre-rinsed with distilled water and the solution to be contained, take 25 ml of the new iron solution and empty it in a conical flask. And as mentioned before, this 25 ml of the solution contains 0.1 of a tablet. Set the conical flask under the burette with a white piece of paper under it to observe the color change. Now you may finally begin to titrate. Release the titrant bit by bit and shake the flask in between goes to make sure it reacts completely. Once you reach the endpoint, record the final volume, refill the burette, clean out the flask, and titrate the solution 3 more times. Once you have done this with the current iron tablet, repeat the steps for making an iron solution with the other brand of tablet and titrate 4 times, getting your results. Once you have gotten your results, you want to discard any results that seem like an outlier and then begin to calculate your mean titer. Once you have your mean titer, you can now begin to calculate the moles of manganese. For this we use the equation N is equal to Cv. Now that we have the moles of manganese, we can determine the moles of Fe2+ using the molar ratio calculator from before, which was 1 mole of manganese is equal to 5 moles of Fe2+. So we end up with 0.000119 moles of Fe2+. We can now calculate the mass of Fe2+, which is 0.0066 grams, and we can now convert this to a weight-to-weight percentage, and compare this to the weight-to-weight percentage on the cover of the tablet. To do this, we must first calculate the weight of 0.1 of a tablet because we only titrated 0.1 of a tablet. To do this, we use the total weight from earlier, which was 2.8 grams, and divide that by 100, because the weight was of 10 tablets. This should give us 0.028 grams for 0.1 of a tablet, so dividing the mass of iron by the weight of the tablet times 100 gives us 23.69% approximately. For my other brand of tablet, I ended up getting the exact same result, which was not far off the mark either. Now for a first attempt, the results are actually quite impressive, as they got near the mark, being off by only 6.31%. The investigation was designed to be valid and reliable as it actually measures the correct value, which is the amount of iron in a tablet as stated by the inquiry question, and is reliable because it was repeated a total of 4 times. As seen from the graphs, the first attempt in both titrations seems to be off by a little compared to the others, most likely due to being the rough titration and me not knowing what mark the endpoint would occur at. After the first attempt, I was able to quickly skip to that mark and titrate slowly to get an accurate result. An issue that was discovered was the concentration of sulfuric acid being too strong to titrate initially, as I overlooked a small detail accidentally. To fix this, I simply just diluted the solution by a tenth to make it easier to titrate. I also had an issue of a loose burette holder which I simply fixed by adjusting a clamp under it to hold it in place. If I could, with some more time, I would prepare the iron solution in a lower concentration of sulfuric acid and allow it to dissolve the tablet overnight. I would also use a proper burette holder that's not broken to reduce any reading errors, as mine was on a bit of a slant, which I guess didn't matter too much as I still got an accurate result. To sum this up, I actually proved my hypothesis wrong by getting close to the actual mark, which is 30% compared to my 23.69%, despite making so many errors while working, which proved to be beneficial in the end. I was able to measure my dependent variable, being the amount of iron in tablets, and my independent variable, which was measuring it for 2 grams, while staying in the parameter of my controlled variables. Now, despite this being a painfully annoying investigation to plan, it is useful in the real world, as it is a method used by food and drug regulation employees to make sure the labels are actually true and not just lying. So I hope you found this as painful as I did to record, and I hopefully get good marks.